Good afternoon. I'm Gustavo Mercado from Argentina, and this afternoon I will speak of looking inside IoT Stack. Um, well, we are going to talk about the study analysis of the Internet protocols that tend to be done through observation, the measures in the documents, standardization standards. This and with a static vision of the network. And this here we propose real measures of protocols obtained in a real network in operation. The objective is to identify methodology that facilitates the study and learning of the protocols of the IoT networks through the observation of real measures generated by those networks in an operation surrounding. And we will be using a laboratory system with the following um, characteristics. It has wireless WSN networks with devices that are microcontrollers with very little memory, scarce performance, and a low potency, uh, low consumption. And here we have a stack, as in the internet, but as it has a very low memory, the devices are generated their own protocol for IoT for these devices that we call restricted devices. If you see it there in the Mac layer, we have a protocol 4 that is standardized, and the R layer we use the 6lowpan that gives the name to this. In the transporter we have those protocols, and in the application we use core protocols. As you see here in these networks, we use IPv6, and here we also have a routing protocol of all that is called RPL. For the router, in the so-called gatekeeper, we use a processor that is a bit more powerful and that has two phases because it's a router. To the one side it goes to the wireless sensors, and on the other to the internet. And finally also a generator with cloud computing and big data that is it's made up of a database server and a software and a server for design and data analysis in this case, and also a broker for the MQTT packets. Now let's see the frames for the analysis. This is the first mesh that we're going to see in reduced form, and here we have the address of source, the destination, the protocol, the length, and the information. For the source information we have the IP version and the origin. This is FE80, that is called link local unicast addresses, and for destination we have an FF02. This is a multicast, and the 1A is all the nodes that have RPL installed in their link local, and the protocol ICMP version 6. It's another transport layer protocol. It is 64 bytes long, and the info refers to the routing protocol RPL, and for the denomination DODAG. In this case it is a request, so that all the RPL nodes of link local may send the node, this FE80, their situation in the RPL routing world so that that node may construct their acyclic graph. And finally, here we have the complete and there you have the details. 1 byte here, that is 41, that is the first packet of the IP layer of this mesh that corresponds to the IPv6 header compression. So let's analyze this protocol. This is a standard that defines the physical level and the control of the access to the wireless networks with low data transmission. And the working group IEEE is responsible for its development. 802.15.4. All the fields are meant to provide information of what the frame is. So we analyze it field by field to see the contents and the definition based on the content. That is what we wanted to analyze. The first is the control frame. The frame control that we won't analyze it here, but in the following. And then we have the sequence number. In this case, it's 111. It's a number that is put in each of the meshes in the frame that correspond to the same sequence. That is used to give them a name going from one end to the other in the same content. Then we have another field that is called destination PAN. PAN is personal area network. The PAN is an identifier of the local network of the system, and it is used. It has 16 bits, and it's used to shorten the MAC addressing. Remember that those have 64 bits each in origin and in source and destination, so it occupies a lot. So if we use it like this with the PAN address, we shorten it because PAN only uses 16 bits, and if we were to use the source of destination, we have to have it visible. So it shorten the destination and the source addresses by halving it. So in destination here it says FF, and that means broadcast in this case, and source is a complete MAC address, 64 bits. And the FCS is here, it tells me that the number is correct. And then let's look at the field of the mesh control with all these fields. First of all, the type of frame. That is a piece of data, and although there are other options, for instance, beacons and clonish, and if security is enabled, in this case it's false, but if it were enabled, then we would use protocol AES 128. This field says frame pending. It means false. It means that there are no frames pending in the same sequence, at least not in destination side. And acknowledge request, it's also false because this frame is data. And here we give the details. If there is an ID compression, PAN ID compression, in this case it's true, as we said earlier. The reserved, it's false. The sequence number suppression, it's also false because there is no suppression. And the information elements present, it's also false because there are none in the mesh. So, and finally, the destination addressing mode is short because, as we said, we compressed it. But there are other 3 possibilities. And the source addressing mode, it's long. It's 64 bits. It's 03 here. And finally, the frame version here is IEEE standard. This field details a standard that was used to build this frame, because they may vary from one standard to the other. In this case, we have 2006, but there's also 2003 and 2015 versions. And in the 6lowpan, 6lowpan, in the first layer of the network, we have a field that is called pattern, that has two subfields. One is the header type and the header length, or the pattern length. In here we have 01. In the chart, you can see that this IPv6 number that appears here, it's an uncompressed IPv6 address, so it's complete. It's the whole thing. And of course, there are low pans to compress IPv6 numbers, so there are other options in the type of header. Speaking of IPv6 compression, the header length is 1 because this is the only field in 6lowpan for this mesh. So 6lowpan was developed by ATF to apply the IP Internet Protocol in the smaller devices, allowing the low consumption devices with limited processing capacity to participate in the Internet of Things. The group 6lowpan defined the encapsulation, the compression of the headers, neighbor discovery, and other mechanisms that allow IPv6 to operate to run in networks based in IEEE 802.15.4. So the issue here is that the MTU of these networks is very small. In this case, is 127 bytes, and each of the headers of IPv6 has 40 bytes. So putting 140 bytes in 127, you are wasting too much. So although it has other qualities, this was used to compress the packets for IPv6 addressing, or routing. So let's see the IPv6 frame. This is a typical frame of IPv6. Here, this is a construction with 40 bytes in the complete case, but it may have more with the next headers. And so let's see each of the frames of each of the fields. Here, this is, version 6. We also have other field that is the class of traffic. In this case, it has two subfields. One is the differentiated services, and the other is the notification of explicit congestion. In the case of the differentiated services, in our case, we have service CX0, that is a standard service. But there are other differentiated services to provide quality of services to the packet. As to this field of congestion, in this case, we have not EC. That means that this node is not capable of determining congestion that is reaching there. It can't measure congestion, so it can't announce it. If it had a node that can measure congestion, then we would use the others. So another one is the flow label. In this case, it's 0. It has no flow label. You know flow labels, right? It's a method to establish a path between source and destination going through the same nodes. As a result, you can achieve quality of service in IPv6. The payload length is 6 in IPv6, and the payload, and in the next header is in ICMPv6 58, and here, for instance, TCP and IGP, hop limit is 64, and let's see the source address. It's FE80. It corresponds within the characteristics of IPv6 to a link local unicast. It means that it only encompasses the link local. It's not routable. And so, therefore, if we want to use something special in that network, such as an internet exchange point and IXP, we're only going to have a link local. And of course, the source, the origin is true, it is forwardable. You can find it. The destination is true. You can find it. No, this packet is not forwardable. You can't take it outside the router because it's in the link local, and it cannot be found from the outside. It's not visible from outside. And finally, the protocol. It's reserved by protocol. It's true because it is. There are blocks reserved for special purposes for IETF.
As regards the destination address, this is a multicast address we see over here. This is a format of the multicast packet that has an 8-bit prefix, 4 bits and a scope of 4 bits and 112 bytes. Now, in this case, the prefix is FF02 and the group ID is 1A, which means that all RPL nodes, all the RPL nodes are the ones that exist in the link local and that have RPL. As regards the prefix, the first is reserved, the second one is a rendezvous point. In this case, this is false because there is no rendezvous point embedded in the multicast packet. The network prefix does not exist because there is no prefix information on the network, and there is no transient. All the multicast addresses are well known. So the scope finally of this packet is link local 02. There are other scopes, of course, node, link, site, and organization, and so on. So this is the analysis of the IPv6 packet. Now let's just look at the analysis of the ICMP-v6 packet. This one is focused on RPL information. This is a routing protocol for wireless networks, low energy consumption, and typically susceptible for packet loss. This is a proactive protocol based on distance vectors and operates on IEEE networks, which is optimized for multi-hops and many-to-one communications and also support one-to-one messages. RPL creates a similar topology to a tree, an acyclic directed graph, and within each network, each has a range assigned to it as the devices are further away from the root node. The nodes forward the packets using the selection criteria for that route. So this is the RPL. Regarding the ICMP, this is a format at the bottom where the type, the code, the checksum, the identifier, and the sequence number, plus the optional data. Regarding the type is 155, which means RPL control. The code is 0. It means that it is a DODAG information solicitation made to all RPL nodes in the link local. So of course, this code can change. It can be one that information is forwarded, that request information is forwarded. This is requested DODAG information. You have 02 code where you have a destination advertisement object when there is a change in another node. And of course, we have the acknowledge. The checksum is correct, and the other data don't exist. So this is the ICMP v6 and the RPL DODAG version. So to conclude, first of all, let me clarify something. This conference has been quite brief because of the time constraints, but of course, we couldn't have a look at the application layer with the COP protocols and MTT protocols. We could have done a sniffer at the exit of the router to check what the internet was like, and would also have sniffed the communications between the database and the graphic option, which is SQL options, and of course between the broker and the client, which also has its own protocol. So this is something we could do right now, but we're almost ready with that part. This paper could be dedicated to a full webinar where you can see the entire sequence. We could also do some live demo. We could work also remotely in real time so that the students can see how packets perform. And finally, we can see that the IoT networks study can be done in a convenient way using real frame analysis produced by devices in operation. The methodology can be used in other network technologies of the IA2, such as LoRaWAN, Sigfox, BLE, Wi-Fi, low LTE, in category M and NB IoT and so on. It is also valid when the 5G technology will be available in our region. With that, we close. If you download the conference right at the end of this last slide, we have the annexes, which include information on the I plus IoT remote lab version in 6lowpan. We also have a brief description of the protocols that are analyzed, as well as references of the protocols. So you can check these out and look at the documents if you wish to further expand your knowledge on this topic. And finally, the rationale, the full rationale of the applications of these methodologies. So thank you very much for your attention, and I'm happy to take any questions.